Good afternoon, ladies and gentlemen. As the last speaker, I will try and gather together some of the threads of the discussion during the earlier talks this afternoon. And I've talked about nanotechnology. You see the book translated into Turkish. My talk now will be called Nanotechnology, Present and Future. And I really want to just briefly look at the areas in which nanotechnology can be really useful right now. We can already start creating manufactured products in the marketplace that are something that everyone wants, actually, because that is the essential prerequisite for any successful business. There has to be demand for what we are proposing. And I'm really going to confine myself to the three big areas, what are considered to be the three big application areas, namely energy, health, and information technology, IT. Let me start with IT, since that's the easiest to deal with. Well, information, people mostly think of very large-scale integrated chips. We've already heard, I think, that the feature size now is around 22 nanometers, I think, and still decreasing. So this is de facto nanotechnology, if we take the international consensus of the nanoscale being between 1 and 100 nanometers. So any device that contains features below 100 nanometers is a nano device. It also, nanotechnology in IT also includes a lot of ancillary devices, ancillary components, things like thermal interface materials, which may consist of nanoparticles, metal nanoparticles dispersed in some grease to solve the heat management problem. The smaller the chip becomes, the more denser the components and the hotter they become. So we need thermal interface materials. And also sensors, because sensors, chemical sensors or other kinds of sensors, any kind of sensor is simply an information transducer. You are transducing photon intensity, a concentration of an environmental chemical into an electrical or an optical signal. So that also belongs to IT, and we also have certainly in the research laboratories a great many sensors. I won't talk about those in detail anymore because it's too big, basically, and too diverse. And it's also running its own path, particularly in the very large-scale integrated chips. It doesn't need any input from us. That has its own dynamism, governed by Moore's law, the International Semiconductor Roadmap. So let me turn to energy. And now energy, of course, is very diverse. And let me remind you, I think you all know, nanotechnology is materials, devices and systems, which is a continuum of increasing complexity. As we get to materials, so-called sensorial materials, that can respond to their environment, then can even adapt to their environment, they have information processing capability, which actually makes them into a device. So there's no boundary between these two, it's simply increasing complexity. But if you think that after about 3 years of deliberation, the International Standards Organization has now more or less completed its project on defining the vocabulary of nanomaterials, and everyone was so exhausted that we said, well, let's leave. We'll start with nano devices. That's the next thing. Originally, it was going to be all nanotechnology, but it was just overwhelming. So, devices are coming. And we're always looking at the paradigms offered by biology. This was already pointed out by Eric Drexler in one of his earliest papers, that we see living proof of principle. In fact, one of the earlier speakers showed one or two examples. That we already have motors, rotary motors, linear motors, muscle, enzymes and so on, working at the nanoscale. So we have nano devices, we have examples of nano devices in the living world. So it's very real, the existence of nano devices in nanosystems. But it isn't yet a reality in the manufacturing sphere, and so mostly we are really talking about materials at the moment, what will be traded, what is being traded on the exchange. And it's really the contribution of materials to energy that I just want to briefly, almost if you think of it as bullet points, just to remind you of some of the things. And at present, there are two areas really. There's harvesting energy, novel devices to locally power portable devices and so on. This is more microtechnology than nanotechnology. But again, it's still very much in the research field. The idea is that we don't need to keep putting batteries into our, or charging batteries into mobile phones and so on, but simply have a little device that may use the mechanical energy, that our surplus mechanical energy, even surplus chemical energy, that our blood is a rich source of chemical energy. This is still, I would say, not still a research area. But when we come to saving energy, we see nanotechnology already everywhere. And in a way, I'm not even going to try to list everything because a lot of it is obvious. So lubricants, if we can make a superior lubricant by blending nanoparticles, metal nanoparticles into base oil, then we will, the material will run, the machinery will run with less friction, less energy will be needed to drive it, it will create less emissions, it will need less downtime for maintenance, etc., etc. So that's a very real contribution to energy. Materials become more lightweight. If a motor car can be made with composites, they use less, then you need less energy to accelerate it and drive it. And turbine blades for wind turbines make them out of lightweight composite materials. And now even we see in the latest Boeing 787, we see that composites, albeit not necessarily nanocomposites, but they presumably will be next, composites have now entered the aerospace domain. And we also have other examples which are really in the nano realm, like light-emitting diodes used for exterior lighting, where you get much more of the electrical input is converted to luminous energy than in an incandescent light. And then, of course, we also have the contributions to energy storage, energy generation, photovoltaics, batteries and so on, where we're not talking about nanotechnology. There's no device that is fundamentally different, qualitatively different. We are just talking about nanification, the gradual scaling down of the internal components. If we can make an electrode that is a tenth of the thickness, then we use a tenth less energy to make it, and so on and so forth. So that is the present status of energy. Now in the future, there are perhaps even more exciting things are coming along, like the complete replacement of pyrometallurgy. Now there's a lot of pyrometallurgy, a big metallurgy industry in Turkey, and as you know, this consists of heating ores up to a high temperature, sometimes even when the reaction is thermodynamically downhill. So zinc sulfide ore, for example, is first roasted to make zinc oxide and then reduced. So this is a complete absurdity. From a thermodynamic point of view, you could use the zinc sulfide as a fuel to generate energy and so on. But there is no, at present, there is no alternative technology. So we hope to make something like the kidney, a nano device, a living nano device that can concentrate metals and other compounds from very dilute solutions and concentrate it, and in the kidney, of course, it's just excreted. But if we look at similar processes in the marine world, for example, the diatoms in the sea, they are concentrating silica and calcium and minerals, elements like that, from tiny concentrations in seawater, and they are making structures, physical structures. So that is, and all at room temperature, at the thermodynamic limit, highly efficiently. So that is the future paradigm of how nanotechnology can dramatically contribute to energy, saving energy. And also in construction, concrete is one of the biggest contributors to CO2 emissions. partly from the process itself, the roasting of the carbonate, but also from the heat that is needed. So if we can replace concrete by diamondoid panels, we not only sequester carbon from the atmosphere, but we also eliminate this enormous energy expensive industry. But at present, it is generally perceived that the most exciting opportunities for novel nanotechnology, commercializing nanotechnology, is in the health sphere. Now, nanomedicine is essentially nanobiotechnology, the application of nanotechnology to biology, to biomedicine. We call it nanomedicine. Let me remind you of the dictionary definition of medicine. The science and art concerned with the cure, alleviation and prevention of disease, and with the restoration and preservation of health by means of remedial substances and the regulation of diets, habits, etc. So health is very broad and encompasses many things, notice including diets and habits and so on. And of course, nanotechnology can actually contribute to all of these. But particularly, we are focusing at the moment on the contribution, the possible contribution onto the remedial substances. And really, again, we've very briefly heard about it from a couple of the previous speakers, the essential points that where nanotechnology can contribute in making drugs more efficient or more effective. There are three big problems. One of them is how to evade the body's immune defenses. So many things could be very useful inside the body, but before they get anywhere near their target, they are cleared away from the body because they are recognized as non-self by the immune system, which is thankfully a highly efficient way of eliminating foreign invaders. So we hope to use nanotechnology. And remember, nanotechnology is atomically precise engineering. So we hope by precisely engineering the surfaces of a nanoparticle, for example, a nanocarrier for drugs, we hope to be able to make it evade the attacks of our immune system. And this is ongoing, and this is already we already have a lot of good knowledge and ideas about how to do it. Another area is how a drug can traverse the many barriers, the many physical and physical-chemical barriers between the initial ingestion, the oral ingestion or by injection or whatever, that there are many interesting drugs that are so lipophilic, so fat-loving, that they are simply captured by various lipid membranes in the body, and then there they stay. They are simply accumulated there, and they never get to where they are meant to get. And again, if we can encapsulate such drugs in a hydrophilic carrier, and sometimes even simple materials like a so-called nanoshell, a hollow sphere of calcium carbonate, can already be a useful carrier for certain drugs. For example, calcium carbonate, if we have a drug that needs to be released in the stomach, but would be decomposed by the enzymes in the mouth, we can encapsulate it in calcium carbonate. It passes through the mouth without any effect, and then is simply dissolved by the hydrochloric acid in the stomach. That's a very simple example of this principle of using nano carriers to encapsulate drugs that otherwise would simply get trapped at some early stage in their journey. And finally, there is the problem of targeting a drug. Most drugs are administered systemically, so the entire body is flooded with these drugs, and even though only one site inside the body is needed for their action, which not only can create side effects, and actually most drugs fail in the late stage of development, not because of their inefficacity against their target, but because there are too many side effects. The side effects are too important. So the great battle in drug discovery is against is all about discovering and eliminating side effects. So probably the contribution of nanotechnology will be far more in helping to control the side effects by these carriers. And we have the whole range of nano objects that we can use as carriers for the drug. We aren't talking about developing new chemicals necessarily, new drug substances, but about how to transport, enable the transport of these drug substances to their targets. And one idea for targeting is simply to coat the carrier for a drug with, let us say, an antibody to a particular antigen that is expressed on the surface of the target. For example, certain tumours have very specific molecules that are only expressed on the surface of the tumour, nowhere else in the body. So if you release the drug, and most anti-cancer drugs, as you know, are extremely toxic to all cells actually, they just have a slight differential toxicity and slightly worse for the cancer cells. So if one can release them systemically inside their carriers, and the carriers in the rest of the body don't do anything because the drug is kept, is enclosed, and then when they reach the target there is some sensorial activity in the carrier and the drug is then released, we have solved the problem of flooding the body with a nasty, rather toxic substance. That's how it's supposed to work in principle. Although there is intense activity in this area, of course, I do hasten to add that the problems are still very difficult, and that there is nothing as yet actually in the commercial as a clinical product available for prescribing to patients. And in the future, of course, we will move towards perhaps even more complicated. Again, we already have to have a sensorial material that releases the drug when it reaches its target. So it's a small step. It's again a continuum to the so-called nanoscale robots that can carry out even more elaborate operations. And of course, particularly big companies are working on the specifications for such robots, which will probably be the size of a bacterium and would contain reservoirs for drugs and some information processing capability and so on. Now, remember the second half of the definition of medicine, that the preservation of health by means of remedial substances and the regulation of diets and so on. Perhaps the greatest problem in world nutrition now is the deficiency of micronutrients. And we see that a classic approach to that by bodies such as the Food and Agriculture Organization has been to promote the use of fortified foods. So, for example, iron deficiency is not only a problem in large parts of the developed world, but even in developed countries. In Great Britain, for example, iron deficiency is rather widespread and it's not a fatal problem, but it contributes to a general loss of vitality. But fortification is actually not a good approach at all, because in fortification, what is the product with which what has been used to fortify is then out of balance with the rest of the diet. And we see that in a number of cases have been investigated now. For example, people say, oh, osteoporosis in middle-aged women, for example, you should give calcium. So if you give calcium, actually, the problem gets worse. The reason is that because you have this imbalance, you have local excess of calcium in the fortified or the tablet or whatever, and this sequesters phosphate. Bone is essentially calcium phosphate. The excess calcium actually sequesters phosphate from the bone and makes the bone even weaker. And that's a general example of how fortification, because of the imbalances it creates, is undesirable. What we would like to promote on the exchange is the use of fertilizers to generate, to compensate for micronutrient deficiency, it's often due to a problem in the soil. The soil has been depleted of metals like iron and zinc and so on. So simply, we would like to encourage the far more widespread use of nano-chelated fertilizers. And there the nano is not in the material itself, but in the process used to create the fertilizer. Nano is process as well as material. And this is a very good way. You can make these nanochelates for a great variety of metals, not only zinc and iron, but all micronutrient metals. And so everything remains in balance. The plant, the food that we eat, actually contains the micronutrients as it should. It was only due to years or decades of over-exploitation of the soils that the soils started to have a too low a concentration of these essential micronutrients. Now, we also have heard in the previous talk something about the safety of nanomaterials, and we have the definition of medicine in mind. You probably are all familiar with the doctrine of Hippocrates, primum non nocere. The first and foremost demand of not only a doctor, but actually, I would suggest, of all of us. We do not wish to create harm to our fellow human beings. It is simply an expression of human solidarity. And of course, any nano-engineer, I would suggest, has no desire to harm his or her fellow human beings. And of course, as an exchange, we strongly encourage all manufacturers of nanomaterials to ensure that their products are harmless, are not harmful to fellow human beings. But nanotechnology presently is definitely suffering from a great, even excessive burden of regulation. And if you compare what happened in the chemical industry, for example, in the European Union we have the REACH initiative just got underway, and we have an equivalent in the USA, the TSCA, the Toxic Substances Control Act. Now, these have only come about relatively recently compared with the entire history of the chemical industry. So the whole industry had a great deal of momentum already, and it can take this on board. But if you immediately, even before an industry has really got started, you already come with enormous regulatory burdens, you will kill off a great deal of the entrepreneurial activity that we actually are trying to encourage. So we definitely need to try and encourage a moderate approach to this question of risk and regulation, and I think our premise should be
you
that
need also nano-regulations.
Well, we do, but not excessively, because the premise.
No, I mean nanoscale.
Oh, the nano. Yes, the regulation should be nanoscale. Very true. Yes, that's a good way to remember it. And remember, risk is the product of hazard multiplied by occurrence, the frequency of occurrence. Because we have so little data, in many cases, we do not know what the frequency of occurrence is. So what is the basis for computing risk if we cannot even quantify it? Now, we have all these tremendous opportunities in nanotechnology, and what do we think will happen now? We have ideas, and we have, hopefully, investment or potential investment. Let me warn against over-reliance on exogenous sources of investment. By far the best way for a company to grow is endogenously, using its internal resources. And again, the exchange, I'm only really emphasizing and repeating what Mustafa has already said, that if there is a market, if there already is a demand for the product that is being produced, then it can be traded on the exchange. And using forward orders, forward selling, then finance is available for scaling up to whatever is required to produce, to fulfill those orders. The other options, of course, are in the case of a very large company, of course, they may have internal resources, BASF and so on. But as we know, the large companies are generally much less innovative than the small companies. The real source of innovation are the small companies, and it's they who do not have these internal resources. And then we have, of course, the venture capitalists and so on, but again, as already been stated, if you let venture capitalists finance your company, then you lose control. They will take equity, and the control that you've lost may be even sufficient to destroy the company, because the aims of the venture capitalists are, of course, different from those of the technologists who founded the company. And finally, there are government funds. But again, if you look at the track record of large government projects, we do not see a particularly rosy picture. We usually see a picture of waste of money, of enormous millions, billions very often, of dollars or whatever, of currency units. And the rate of return is sometimes like 0.5% or something like that, way below, if it is positive, way below anything that a normal commercial enterprise would expect. So, of those 4 ways of financing a nanotechnology operation, internal forward-selling, venture capital and government funds, the forward-selling approach, which the exchange has formalized and enabled now, is by far and away, I would suggest, stands out as an outstanding way in which an industry can really grow. And of course, one of the great beauties of that approach is that it does depend on there being a market for the product. Whereas in most other cases, that can be forgotten. If there is a lot of money from the government or so on, one doesn't necessarily need to worry about that most important question: does anyone want to buy? Is it something that people want to have? And so that is the most important role of the exchange. And the other one, really, I said we have ideas and investments, it's the future of nanotechnology. The other is, in a way, exchanging ideas. So we have, for example, one of our members is a producer of nanoscale copper. But he did not know that it could be used as a lubricant. And another of our members or other members are producers of base oil, and they also conversely did not know that they could enhance their product by incorporating nanoscale copper into the base oil. So the exchange can also bring together producers in completely disparate areas. Normally base oil and nanoscale copper, they are poles apart on the spectrum of products, and yet now we can bring them together to make a nano-enhanced lubricant that will of course contribute to energy saving and many other things as well. And the other advantage of that kind of new product, which is absolutely legitimately called a nano product, is that it is essentially a sort of product of substitution, which are always, industrialists always like products of substitution, because then you don't have to redesign your entire supply chain. So that is, I think, in the immediate term, that is where we very much see nanotechnology developing, where we can incorporate nanotechnology without overturning the whole industry, the so-called disruptive technologies, which sound very good and people are very excited by them, but there is a great resistance to their implementation because too much existing infrastructure may need to be destroyed prematurely or redesigned, which is also expensive and would have then to be factored in to the possibility of implementation. So on that note, let me conclude. Thank you for attention.
Do you have any service giving advice to the companies and to meet them to make a better product or lowering the cost, something like that?
Yes, yes, we do. It's on an ad hoc arrangement. So any company wishing that should contact us, and then we will be very happy. Yes. To offer such a service.
Hearing that this is very good for the industrial producers, you know. So we have some some necessity to change our product or add some more facilities, then we can ask you what kind of nanoparticles we can use it and how we can use it.
Yes.
If you know what you want to achieve, which areas that you want to improve, then we'll look at the possibilities of what there is already is on the market that we could introduce.
Okay, thank you. Thank you for the presentation.